As I've mentioned all along, the small signal method is extremely important and one of the key techniques used in EECS and our industry overall. So I'm going to look at it from a whole bunch of ways. Okay, we already looked at it from an analytical view. We also looked at it using the Zen approach. And then now let me look at it from a graphical point of view and try to help you gain some insight into what this delta VD and capital VI and so on really mean in when interpreted from a graphical point of view. Okay. So you recall our device had the device equation ID being equal to f of VD, where that was A e raised to B small v capital D. So from a operating point of view, I replaced ID and VD in that equation with the operating point values ID and capital VD. And so I got my operating point equation that I show here, ID equals AEB VD, where all the variables are in caps. That's my operating point. And then we said that my small signal ID was related to the small signal VD by proportionally, and it was in fact related by multiplying small vd by a constant, and that constant IDB was the slope of the function at the point capital VD comma ID. Okay, so that was the slope at the VD ID point of the ID equals f of VD curve. So what I'd like to do next is give you a graphical interpretation of exactly what this means. What are we exactly trying to do? And hopefully this insight will be the last piece of insight you will need before you really understand what's going on. So I'm going to use this curve here. So this is my 0 point, and this is my relationship between the current and the voltage for my export weave device. Okay. So what exactly am I doing? So the first step of the small signal method, I said you start by picking some operating point and you operate the circuit at that point. I call that the VD ID point. Okay, so that's my DC bias point, and so this was the operating point. Operating point. Next, what I did is I said in the method, let's choose a small variation, choose a small input. Okay, so we picked a really small input. We call that small v, small d, and we said, let's try to find out what the output of this looks like. So the output was ID, and to find out what ID looked like, what I said we're going to do is take the slope, okay, take the slope of the function at the point VDID. So this is the point VDID. So let me write down the slope of the function. This is the slope at this point. So that's the slope of the function at this point. So let me call that the slope of the f of VD function at the point VDID. So I picked the point, I got the slope, and then I chose small vd. And if I take it up here, if I plot my point, what does it mean to multiply the slope times the small variation? Okay, so what it means is if I take this slope and I multiply it by the small variation, what do I get? Notice the slope is the ratio of this piece divided by this piece. Okay, so if the slope is s and this piece is, let me call it y, and this piece is z. So if this is my s, this is y, and this is z. And if my slope s is y divided by z, then what is slope times small vd? So the y is my small id. So y is the small change. Z is a small change in VD. And so slope times, if I multiply the slope times Z, then I get a Y. Okay, so Y is slope times Z. So therefore, if I multiply the slope here times Z, I'm going to get the small variation Y. Okay, so interestingly enough, what I'm doing is by multiplying the slope with VD, I am getting this as my ID. All right, so again, by taking my slope S and multiplying that by VD, which is marked that as Z here, I'm getting Y. Okay, where Y is my ID. Okay, so what I've done is I've approximated the actual value with this point. So let me mark that point as B. So I'm using B as the value of ID. Okay, so I'm using this little length here as ID. But really, what should have been the right value? If I'd actually used to be actually correct and fair, I would have had to go up here and pick this value. Okay, let me mark that as A. That value up there, A, is the actual point that I should have picked. Okay, what I've done is I'm ignoring this little delta here, the small difference between A and B, and I am using B as my approximation. Okay, this is nothing more than a graphical interpretation of the whole Taylor series method. So in this little example here, all I'm doing is I'm approximating A with B. Okay, that's the basis behind this method. Okay, so finally, before we move on to seeing how we can build circuits using this method, what we've done so far is we've introduced a small signal method, and I've shown you how to view it graphically. I've shown you how to view it mathematically. So as a next step, what I'm going to do is talk about circuits. As we've been doing throughout this course, I kind of give you the conceptual understanding. Okay, I give you a graphical understanding. I give you the conceptual understanding using either graphics or other forms of conceptualization. I show you how it works mathematically. But then we end up usually taking a circuit view, and the circuit view tends to be really, really simple. Okay, where you can practice things much more easily with the circuit view, and as long as you know how it works mathematically with the circuit view as a practitioner, you can do some things very, very quickly. But it's always good to understand the mathematical foundations behind what you do. And when I show you the circuit method, you'll be amazed at how simple this whole thing really is.